we've already looked at hypothesis testing, so you have a background on what the steps are that you'll take to do a hypothesis test. In this section, we're going to talk about doing a hypothesis test with two groups that have two different means. So, for example, if you wanted to test a claim involving two groups of people and the type of breakfast they eat, and I would take a group east of the Mississippi and west of the Mississippi, we'd have to use a different technique because we're comparing two unique groups when doing this hypothesis test. So we're going to learn to do these by type. We're going to learn to conduct and interpret several different type of tests for two population means, depending on what information we are given in the problem itself. So the first question is, if I have two independent samples, and they're simple random samples from two distinct populations, to meet the criteria to perform this test, I need a sample size that is small, where the distributions are important and they should be normal, and the sample sizes are large, then the distributions are not important, which means they need not be normal. So basically this is a caveat, right? So if I did a simple random sample and my sample size is really small, I need to make sure I have a normal distribution. If they're very large, I don't have to take that extra step. The test that's going to compare the two independent population means with unknown and possibly unequal standard deviations is called the Aspen-Welch t-test. We typically are just going to call this a t-test. And the degrees of freedom formula gets its name from Aspen-Welch, hence its name. So we would use this test when I have two groups with population means and I have an unknown or unequal standard deviation between those two groups. That's when we do this. So in this method, I have a difference of means that I can calculate by taking the mean of the first group and subtracting the mean of the second group. Because we don't know the population standard deviation, we have to estimate them using this estimation method. So we're going to calculate an estimated standard deviation, but you're going to notice it's going to be called a standard error in most places, and we're going to utilize the difference of those means to do so. So I'm going to take my S1 squared divided by my population number of values, my S2 squared divided by that, and that's going to give you my standard error. Then to get the test statistic, which I will compare to the critical statistic, I'm going to utilize this formula. Now, what do these different variables mean? S1 and S2 are the sample deviations and they're estimates of the population standard deviations. These are our unknown population standard deviations. So I don't know the standard deviation of my population, but I have the standard deviation or an estimate of it for my sample, which should make sense. Then I have the sample means, and mu is the population mean. So when you're working these problems, you've really got to dig into, is this my sample or my population, and make sure that you're using the appropriate piece for that formula. Then we have something called degrees of freedom, which requires a little bit of a complex calculation. Technology will do this calculation for you. And so when I'm doing this, degrees of freedom is not always a whole number for this. As you see, there's a lot going on in this formula. So this is okay if we don't get a numeric degrees of freedom. So let's look at an example. Here I have example 10.1. I have an average amount of time boys and girls, so two different groups, 7 to 11, spend playing sports each day, and it's believed to be the same. So that's what I'm looking to test here. A study is done and data is collected that results in what's given in this table. I want to know, is there a difference in the mean amount of time boys and girls play sports each day? And I want to test that at the 5% level of significance. So to do this, I don't know my population standard deviation. Notice this says sample size, average number of hours, which is a mean, guys. So I don't know this. So this means I'm going to utilize this method. So I'm going to use G and B, G for girls, B for boys, makes sense, right? As the subscript to make sure that I'm working with the correct numbers. So then the mean of population would be mu sub G and mu sub B would be boys. And so this is a test of two independent groups because boys and girls don't have overlap, two population means because I'm trying to generalize something here from my sample to a population. So I'm going to have a random variable where I subtract the sample means, and that gives me the difference in the sample means. My hypothesis, my null here, is that my populations are equal, and my alternate is that my populations are not equal. Then, if they're equal, that means that when I subtract them, I should get 0. If they're not equal, when I subtract them, I won't get 0. So this is a really different step in the hypothesis step. The words the same would tell us that they're equal. So that's where I pulled that they're equal from for my null hypothesis. Since there are no other words to give me the alternate, I'm just going to assume that they're going to be different, and it's going to be a two-tailed test because of equality. So as I start digging into this, I'm going to start labeling things, and I'm going to have my sample standard deviation for girls, my sample standard deviation for boys. I'm going to subtract my mean to get negative 1.2, and half of my p-value is below negative 1.2 and half is above. So that's where these critical values are coming from, is taking that difference between the mean. Then I'm going to use technology. You don't have to use a TI calculator at all. That's not required. You can do the calculation by hand, or you could use StatCrunch or another online calculator. And I'm going to calculate my p-value. And in this case, my p-value is going to be in the range where I'm going to reject it. So I'm rejecting that the mean time for girls and boys is the same, which means they're different. Now, I don't know how much they're different. I just know at the 0.05 level of significance, they're going to be different. And you got to make sure you recognize from your distribution how you're coming up with the 1.2 and the negative 1.2 from the distance of the means. Now, if I have two population means with a known standard deviation, so this time I know the standard deviation, I have some different formulas. So this time I'm using this big formula. My standard deviation looks very similar, except for now I have the population plugged in here, and then my test statistic is going to be a z-score. So let's see how that looks when we do this one differently. So I have independent groups, and the population standard deviation is known. So looking at my table, I know my population standard deviation. I want to look at both populations having a normal distribution. That's good. And I have the data recorded in this table that I could click on if I wanted to from this text. Does the data indicate that WAX 1 is more effective than WAX 2? And I want to test that again at the 5% level of significance, which is pretty standard. So here, I'm going to look at, I have two independent groups, two population means, and I've got a population standard deviation that is known, okay? So my difference of my means would be x1 minus x2, or x bar, however you want to pronounce that. And my null hypothesis is that the mean of the first group is less than or equal to the mean of the second. And the words more effective is what gives me that. More effective means that WAX 1 would last longer than WAX 2 on average, longer being the greater than symbol and goes into the alternate hypothesis. Because remember, the alternate is what we're wanting to happen here. So because it's a greater than, it's a right-tailed test. And so I can look at my difference of my means. I can calculate this out. Since my mean is less than or equal to my mean 2, the difference between those two means should be less than or equal to 0. So I'm going to calculate my p-value, and I get this for my p-value. And if you look at your graph, I get a p-value of 0.01799. And my critical value from subtracting the two means that I have is 0.1. So now I'm going to compare the alpha level and the p-value. So my alpha level of 0.05 is going to be less than my p-value. So I do not reject the null hypothesis because it is less than my p-value. So that's what helps us make that decision. Again, the p-value can be calculated using a whole bunch of different methods. I could use the hand calculator to crunch it. I could use technology. I could use a website. Okay, let's look at two means and two proportions.